Hi everybody, welcome to homework worksheet number 6, problem 4, presented by Annie, Chris, and Anna. Today we'll prove that if a function is integrable on some closed interval, then for all elements in the real numbers, any scaled version of that function will also be integrable upon that domain. So since the function is integrable, we know that the upper integral and the lower integral of that function will be equal by definition. We also know that for all epsilon greater than 0, there must exist a partition such that the upper sum minus the lower sum of that function will be less than epsilon. So this proof has 3 parts. First, we'll look at what happens when that real number is equal to 0. Then we'll look at what happens when that real number is positive and ultimately negative, so that we can prove for all real numbers. So if we let c equal 0, well, c times the function is just simply going to equal 0. And when we look at the upper and lower integrals of that function, cf, we're really just looking at the upper and lower integrals of 0. So since they're both equal to 0, they equal each other, and hence, by definition, since the upper and lower integral are equal, cf must be integrable on the closed interval ab when c is equal to 0. So now we need to look at what happens when c is greater than 0. And in this case, remembering that the function is integrable, we know that for all epsilon greater than 0, there must exist a partition such that the difference between the upper and lower sum will be less than epsilon divided by that element c. So what this tells us is if we write our upper sum and we compare the upper sum of the function to the upper sum of c times the function, we can actually factor that c right out of the series sum that it represents. And if we recall, the upper sum is really just the series sum of all the supermums with respect to the function. So the lower sum will hold the same properties here, and we'll be able to basically factor out a c from the series sum of all of our infimums of the function. So now looking at this situation a little bit further, if we look at the difference between the upper and lower sum, and we can prove that this is less than epsilon, then by definition, cf must be integrable on that domain. So based on what we just defined, we can rewrite the upper and lower sum as c times the series sums of the supermum and the infimums. And when we take the difference between the two, we can go ahead and factor out that common factor c. And now what we can do here is replace what this stands for. So we have c times the difference between the upper and lower sums of the function f, not cf. And we, by definition, had stated that the difference between the upper and lower sums would be less than epsilon over c. So by factoring out that c from the left-hand side, we can bring it over to the right-hand side and basically multiply that first inequality by c to be left with the fact that the difference between the upper and lower sums of cf is actually less than epsilon. And by definition, cf must be integrable upon our closed interval ab when c is also positive. So far we've proven for 2 cases. We've got one more to go. So this one was a little bit more challenging, looking at what happens when c is negative. So we're going to start with the same concept here. Since the function's integrable, we know that for all epsilon greater than 0, there must exist a partition such that the upper sum minus the lower sum of that function is less than epsilon over the absolute value of c. By doing this, we can still use this proof in its totality because the right-hand side of this inequality is still greater than 0. So by definition, we know that our capital Mi's represent the supermum of our function, and our lowercase mi's represent the infimum of our functions upon a certain domain. So we know the following inequality is true just based on the definition of what we're working with. We know that in a usual situation, our infimum would be our lower bound, and our supermum would be our upper bound, with our function floating in between. But when we multiply this inequality by c, what's going to happen here is that our inequalities are going to reverse direction. So writing that, starting with our lowest value first, cmi, our greatest positive, now our smallest negative, becomes really, in essence, our infimum, and lowercase cmi becomes our supermum of the function c times f of x, when c is negative. So if we look at the upper sum of cf, notice that we have to use lowercase mi as opposed to uppercase mi as before. And we can still factor out that c of that, outside of that series sum. And now we can do the same for the lower sum of CF. And now notice here, C times capital MI is now the infimum of our function. So now we can rewrite our series sum as shown, and once again factor out that C. So now putting this all together, when C is negative, when we look at the difference between the upper and lower sums of CF, what we can conclude is rewriting the upper and lower sums as series sums, and once again factor out that C. Now, this is where things get a little different than before. If we really want to be able to state the right assumptions, we really need to have capital MI being subtracted from, have lowercase mi actually being subtracted from capital Mi, our infimum and supermums. So here what we're going to do by taking the absolute value of C, it's like we've multiplied the outside of the function by -1. And we can ultimately do the same inside this expression. In doing so, we can reverse our negative sign, our subtraction sign, and be able to state this as true. Now let's think about what we started with. We knew the difference between the upper and lower sum would be less than epsilon divided by the absolute value of C. So now we can state the following assumption here as well, as though we were multiplying both sides of that stated inequality by the absolute value of C. So in doing so, notice that the absolute value of C will cancel out, and we will be left with the assumption that looking at the upper sum of CF and comparing to the lower sum of CF, if we take the difference, we can now say that that's less than epsilon. Therefore, CF must be integrable upon this domain when C is less than 0. Now, since we've proven it for all cases, we can finally state, since we validated all of our results for any number as an element of the real numbers, we're left with now knowing that if we have an integrable function on some closed interval, then for all real numbers, any scaled version of that function will also be integrable upon that same domain. Thanks so much.